Alright, today we're talking about limits. We're talking about particularly the definition of them. We're used this to describe like relations between instantaneous speed. And we'll talk about one-sided and two-sided limits. Sandwich theorem we won't get to in this video. I'll post a separate video about that. When we're talking about instantaneous speed, okay, or average speed, we're talking about total distance over total time. I'm using y to define my distance here, like I'm using y to relate my distance. So if you remember that gravity is 32 meters per second squared, 9.8 meters per second squared, or 32 feet per second squared, may not have known that 32 value. But if you remember from physics, those formulas like 1/2 gt squared, that's your displacement equation, or your just your distance that you travel. Okay, so if you plug in 2 into your that equation, that's your total distance, which is 64 over total time, which is 2 seconds. So it's 32 feet per second, but it's a falling object. That doesn't make a ton of sense in this scenario because, I mean, falling objects don't fall an average of anything. They just speed up over time. So we want to talk about instantaneous speed. The problem with an instant is that that's not a 2-second interval. 2-second interval isn't an instant. Maybe like a tenth of a second or a hundredth of a second or a billionth of a second, like a nanosecond will work out. So if you look at this equation, it might look a little weird, but where that h is how far past 2 seconds we go. So how far past the instant 2 we go. If you see if we go 1 second past 2, the first value in our table, I mean, even 1 second's not an instant. That's too long. But if we did over a 1 second interval, it would go 80 feet per second. But if you go a tenth of a second, hundredth of a second, thousandth of a second, those are really small time intervals. They're getting closer to instants. So instead of 32 feet per second average, it's about 64 feet per second at that instant of 2 seconds. So right at 2 seconds, it's going 64 feet per second, which is a better gives us a better picture of what actually is going on there. So if you notice, we're taking these values as h approaches 0, if you can think of it that way. Because you can't put 0 in, you'd be dividing by 0, but we can make h really, 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 really small. So if we take the limit as something approaches 0, and that something we're making approach 0 is the x value, that limit is the y value that you get close to. So I'm calling that L. So look at here. We have the limit of sine of x over x. Again, you can't plug in 0. You get an error, which you see in the little table here. But graphically, you can see that thing kind of hits 1. And also the y values do that too. So if you notice, you take negative 3/10, negative 2/10, negative 1/10. If you took negative 0.0000000000001, you'd probably get 0.9 repeating. Actually, your calculator would probably give up and just start routing all those 9s into 1. So it would say that, oh, the y value just seems to be 1. So that's what a limit is even if we can't take the x values that we care about, we can take them really close to that and get a limit. So here, these are 3 different examples of, what the difference between a limit and a function value. So this is actually if you notice, there's a polynomial function at second degree over first degree, and actually makes the thing appear linear. And it's because that if you factor that, the x minus 1 would cancel out, so the little hole that you have could cancel out. But in the first one, your limit as x approaches 1 is 2. The second one, the same thing. The limit as x approaches 1 is 2, but it has a function value, because it's a piecewise function, at a different place. One is just a regular limited function. Now the first one's not defined at 1. The second function, the one in the middle, is defined at 1, but it's a different value. Some trivial information here: the limit of a constant function is just that constant value. So the limit of the constant function pi is just always pi. There's the limit of the constant function y equals 7. Well, the limit's always 7. And for an identity function, the limit's always the domain value you get. Those aren't terribly important. Those are really trivial things. The properties of limits, things you can do with limits, just know that you can do this. As long as you're taking it the same x approaches the same thing, you can add limits. Okay? The difference rule is just you can subtract limits. So if you take a function that's 2 things subtracted, you can separate it. You can multiply them. You can multiply them times a constant. You can also factor a constant out, which is going to be used. You can divide them as long as in the bottom thing isn't 0 at that particular value that you're approaching. So if one of the limits on the bottom is 0, that gives you a problem. And you can actually even raise them to a power. So if you have a function raised to a power, and you know what the limit as x approaches that function, then you just raise the limit, the limit itself to a power, and you're fine. When we're looking at using these properties, okay? Now, for polynomial functions, they're defined everywhere. The polynomial functions, we're not really going to use limits for there, but it helps us get the concept. You could just plug in c, as you see I'm doing here. I'm just plugging in c into the x. Now, when you can do that, it makes you seem like, well, that's pointless. That's just a function value. Well, that's not what we're going to use limits for, but it's here to drive home. All right, c is that c, the x that you're approaching, is an x value. A limit itself is a y value. Okay? Right here, this is just driving home when we're talking about for polynomial and rational functions, since they're defined on all real numbers, the limit as x approaches c is just the function value c. But that's true for polynomial functions and even rational functions, as long as, again here, as long as your denominator isn't 0, then that's true, but that's not what we're going to use limits for. Again, just to help you get the notation, what we're going to use limits for is for things that behave badly as we approach a particular x value. But if they behave nicely, you can just plug in, here the x value is a number, right? We just plug in that 3 into there, calculate it, and you get down your limit. You can do the same thing here, just plug in the number. But here, you can't do that same thing. Take the limit as x approaches 0, we have a problem. We're dividing by 0 here. And I can see graphically, man, it looks like this y value as x approaches 0, it looks like the y value is like 1. But, alright, so I write out tangent of 0 over 0. It's not going to be fun, but I do remember that tangent is sine of a cosine. So they say, hey, use that product rule. Well, I'm going to try to use the product rule. I'm going to separate into sine over cosine. Oh, but I got to account for that x in the denominator. So if you remember, we did the limit as x approaches 0 of sine of x over x. We did it kind of doing those tables, so it's actually a good thing. That's going to be something you're eventually going to memorize, and we can prove that using the sandwich theorem, which I'll do in a separate video. But since x, sine is bounded between 1 and -1, and it happens to works out like that. But the limit as x approaches 0 of sine of x over x is 1, so I can replace this thing right here with 1. And the second one, you can actually just plug it in. It's 1 over cosine of 0. Cosine of 0 is 1, so 1 times 1, you get 1. Okay, so that's using that product rule practically. When we talk about non-existent limits, well, here, if you notice, as you approach 2 from the left or the right, like you see that vertical asymptote? All right, so if you approach 2 from the left, see how it goes to negative infinity? It plummets. All right, so you could say the limit as x approaches 2 from the, I'll write a negative subscript to indicate that, oh, that's from the left. That's what that means. If I want to say the limit as x approaches 2 from the right, I'm going to do a positive subscript, because that's like from the positive side. You can think of a number line. Negative numbers on the left, positive numbers on the right. So it seems to explode up. It just blows up. So one says negative infinity, one says infinity, and they don't agree. So the limit as x approaches 2 does not exist. So you have a one-sided limit, a left and right-sided limit. You don't have a general limit, a two-sided limit. So your one-sided limits are, we talk about right-hand and left-hand limits. The right hand has the positive superscript, left hand has the negative superscript. Two-sided limit is just that general limit itself. So, and just remember this, for a two-sided limit, you need, for your limit in general to exist, I call it a general limit instead of a two-sided limit. For the limit as x approaches c in general to work out, the limit as x approaches c from the left, and the limit as x approaches c from the right, all have to agree to the same limit. If they don't exist. So here's an example. Look at your bad points. Your bad points are where, you look at 1, there's a break in your graph, which is, kind of an alarm right there. If we approach 1 from the left, you get 0. If you approach 1 from the right, you get 1. So what does that mean if you approach 1 in general? Well, 1 says 1, 1 says 0, so that does not exist. So your limit does not exist in that place where you have that break in your graph. Let's look at 2, though. Again, we have sort of a break in our graph, like there's an open hole. All right? If you approach 2 from the left, and you approach 2 from the right, you actually approach that same little open hole. It does have a limit. Now the function value is off. The function value f of 2 is equal to 2 instead of the limit as x approaches 2 being 1, but it still works out. Sandwich theorem, we'll get into another video.
That's the end of this part of the lecture. Yeah!